So we just introduced the notion of operators and we discussed that operators in quantum mechanics have a matrix representation. And this is not always true. There are operators that do not have any matrix representation, like the position operator and momentum operator. In general, all differential operators do not have any matrix formulation, but many operators do. And it is usually easier to study the mathematics of operators in the matrix setting before we move on to differential operators. So let us try to understand as much as possible about operators using the knowledge of linear algebra and matrix analysis that you already know, and then we will generalize to function space in the next week. Okay, all right. So today we will formally begin with the definition of what a linear operator is in quantum mechanics. Linear operators in quantum mechanics. Okay. Now, in general, an operator acts on a vector in a linear vector space and transforms it into another vector in the same linear vector space. Now, the last part of this line is very important. Okay, an operator should not act on a vector and give you something that does not live in the linear vector space. It should give you always something that still is a vector in the linear vector space. It could be another vector. In general, it is another vector. So I will denote operator by a hat on top of it. So if I write, oops, excuse me. If I write something like K with a hat on it, I'm dealing with an operator K. Okay. Now, why do you need operators? Well, if you simply have a linear vector space with the vectors floating around, it's a rather boring space, right? So you need something that does something to the vectors. You need something to push the vectors, pull the vectors, stretch the vectors, compress the vectors, rotate the vectors. You want to do all sorts of things on this vector space to make it a dynamical entity. Okay? You want things to change as time evolves. When something changes as time changes, the quantity is said to be dynamical, as you very well know. So operators are objects that accomplish this. They serve to change vectors into one another. So K acting on alpha, a vector alpha in a linear vector space, in general gives you another vector alpha prime that also lives in the same vector space. So alpha and alpha prime belong in the linear vector space V. Okay, this is a symbol. The script V is a symbol for linear vector space, LVS. Okay. So what is a linear operator? What does the word linear mean in the definition of linear operators? Well, it's actually quite simple, and it will be hard for you to guess an operator that is not linear. But the formal definition of a linear operator is as follows. Linear operator. Suppose if I have an operator K that acts on a vector A times alpha. As you know from the axioms of linear vector space, if I multiply a vector by a scalar, I get another vector. So A times alpha is also a vector. If K acts on A times alpha, it is the same as A times K acting on vector alpha. In other words, the operator doesn't care about the number, it only cares about the vector. And this is a trivial operation, of course, but a more important one is K acting on a linear combination of vectors. K acting on a linear combination of vectors A times alpha plus B times beta is the same as the linear combination of K acting on the individual vector. So this is the same as, from the first rule, K acting on A times alpha is A times K acting on alpha. So this is the same as A times K acting on alpha plus B times K acting on beta. Okay. So this is what the linearity in the phrase linear operator means K acting on a linear combination of vectors is the same as the linear combination of vectors gotten by the action of K on each one of them. Okay. So this immediately tells us something very nice about operators. Since you know that suppose if we have a set of basis vectors EI, excuse me, every vector alpha can be written as a linear combination of the basis vectors, right? So what is this? This is equal to A1 E1 plus A2 E2 plus blah blah blah. Yeah. So the vectors, the basis vectors EI are set to span the space, right? This is a complete set of basis vectors. Using the terminology that we learned yesterday, this is a complete set, or these basis vectors span the linear vector space. So if K acts on this alpha, this equation can be recast as K acting on I equal to 1 to whatever. So I'm not going to write that. AI, EI, or in other words, this is K acting on A1, E1 plus A2, E2 plus so on and so forth. And using the definition of linearity of this operator, this can be written as A1 times K acting on the first basis vector plus A2 times K acting on the second basis vector, and so on and so forth. And I can write this equation as AI K acting on the basis vectors. Okay, so usually in order to understand the action of K on any vector, it is important to know how does an operator K act on the basis vectors. If you understand what this action is, you understand pretty much how the operator acts on any vector in the linear vector space. So this stuff is quite important. And as you know, if K has a matrix formulation, then the matrix elements of A depend on the choice of basis, as we discussed at length yesterday. Okay. Now, this is something that you should keep in mind. Operators in general do not commute. In other words, if you have two operators K1 and K2, then the action of K1 times K2 on alpha, this should be understood as first acting K2 on alpha and getting some vector, and upon that vector you act K1. But this in general is not the same as K2, K1 acting on alpha. Okay, I can write this as an operator equation. The operator equation, or operator inequality rather, is that K1, K2 is not equal to K2, K1 in general. There might be operators K1 and K2 for which the order in which you act the operators on the vectors does not matter. In other words, they do commute, but in general, they do not commute. For example, rotations. Okay. Suppose if I rotate by some angle theta 1 along the x-axis, and I rotate by some angle theta 2 along the y-axis, this is not the same as rotating by theta 1 along the x-axis first, followed by a rotation around the y-axis by an angle theta 2, right? This you already know. If you don't know this is very easy to prove to yourself and satisfy. Simply write down the rotation operator. Okay, you write down the rotation matrix, which you already know. If you don't know how to guess the rotation operator, here's a convenient way. So suppose if I'm dealing with a rotation around the z-axis, right? Now, if I rotate around the z-axis, I do not do anything to the z component of a vector. So if I don't do anything to the z component of a vector, then the last row and last column has to be 0, 0, 1, 0, 0, 1. Why? Because the last 3, 3 component multiplies the z component of any vector. So if the z component should not change, that guy should be 1 and nothing else should change the z component. The x and the y components are mixed together by the usual cosine theta minus sine theta, and cosine theta. Okay. If I'm dealing with rotation on the y-axis, then I should keep the y component of a vector constant. So my second row should be 0, 0, 1, and my second column should be 0, 0, 1. If I'm doing a rotation around the x-axis, then the first row should be 1, 0, 0, and the first column should be 1, 0, 0. So on and so forth. The other one should be cosine sine multiplied. Okay. So using the formulation of rotation operators, you can easily convince yourself that a rotation around the x-axis followed by a rotation on the y-axis is not the same as the rotation around the y-axis followed by a rotation around the z-axis. In other words, rotations in different directions do not commute. Of course, if I do the rotation around the same axis, they do commute. So ry theta 1 times ry theta 2 is the same as ry theta 2 times ry theta 1. Okay, around the same axis, because you're rotating around the same axis, the operations do come. All right. So suppose if this linear operator has a matrix formulation, then if you specify the basis EI, the matrix representing the operator is uniquely specified. Okay, what are the matrix elements of the operator in this basis? The matrix elements Kij of this operator are Ei, K, Ej. Okay, these are the matrix elements of the operator. Of course, if I move to a different basis, the matrix elements will change. Okay. All right. Any questions about any of this up till now? Questions or comments? Okay. All right. So now we move on to understanding how to push and pull bra vectors. So thus far we have dealt only with ket vectors, right? K, so K acting on ket alpha. Now suppose if I have, suppose you know K acting on alpha gives me the vector alpha prime in an LVS. What is the corresponding action in the dual linear vector space? How does the corresponding operators act on the corresponding bra vectors? Well, let us try to figure this out. Suppose if I write K alpha, this is just a notational convenience. It is not a very good notation, I will accept, but it is convenient for me to express things in this notation. So the vector K times alpha, I will write as K alpha. Okay. If I write K times alpha, this is to be understood as the vector gotten by acting the operator K on the vector alpha. Since K acting on the vector alpha is another vector, this vector I am denoting by the vector K alpha. Okay. This is not a notation I will frequently employ, but I'm going to employ it in this class and probably the next to make things a little easier in terms of derivations. Okay. So what is the corresponding action in the dual space? Well, every ket vector becomes a corresponding bra vector. Now the operator obviously doesn't stay the same. The operator that acts on the corresponding bra vector will also change. And this operator, so suppose if I take the dual space analog of this equation, dual space analog, this is going to look like alpha k dagger. And this gives me a new bra vector, which I will call bra k alpha. Now, the first part is should be simple. If I take the adjoint, loosely speaking, of this vector, then the ket vector alpha becomes the bra vector alpha. But the k, there is two changes that you have to notice in this equation. The k becomes a k dagger, and now the k dagger is written on the right of alpha, where bra alpha. In the first equation, the operator k is written on the left of the ket vector alpha. In the second equation, the adjoint of the operator k dagger is called the adjoint of k. Okay, the adjoint is written to the right of the corresponding bra vector alpha. This is one change that you have to note. Now the right hand side is the same. The ket vector k alpha is written as a ket vector, sorry, the bra vector k alpha. So what is the adjoint of k? Suppose if you have an operator that does something to the ket vector alpha, then what is the operator that does something analogous to the corresponding bra vector alpha? I'm sure you can guess the answer to this question, but I will work it out from first principles because it will teach you how to manipulate these kets and bras a little more effectively. So let us start by asking, if I know, suppose I know the components of k hat in the EI basis. Suppose I know kij. What are the components of the adjoint operator in the same basis? In other words, what are the components of k dagger ij? This is the question I want to answer. Okay. So once I know what the matrix elements of k dagger are, I know about the operator because I can write down the matrix formulation of matrix form of the operator. So let us write this out explicitly. K dagger ij, just like kij is given as ei kej, k dagger ij would be given by ei k dagger ej. Okay, if there's any questions about any of the manipulations I'm doing, or if I'm going a little fast, please send me a message or just shout stop. Okay, so I can stop and redo it. So these are the matrix elements of k dagger. Okay, all right. Now, how do I understand this? Remember that the bra vector ei and k dagger should be understood as the k dagger in this equation. The k dagger is acting on the bra ei, right? According to this boxed equation, right? So I can equally well write this as using this notation, the bra ki overlap ej. Okay, this is the same as this using the boxed green equation. I hope this is easy to follow. Now, what do I know? What do I not know? I know the matrix elements of K. I don't know the matrix elements of K dagger. Well, no worries. If I can convert this into the K acting on the ket EJ, I'm done. But I know that in general, for two vectors alpha and beta, the inner product of alpha beta is the same as the inner product of beta alpha complex conjugate, right? This is the fundamental definition of inner products that we discussed when we talked about inner products. That if you have two vectors, the inner product taken in one direction is not the same as the inner product taken in the other direction. It is the complex conjugate of that. Of course, for real vectors, it doesn't matter. But in general, for vectors with complex coefficients, alpha beta, inner product alpha beta is the same as inner product beta alpha star. So let us use this fact in the above equation. So k dagger ij is k ei ej, but this is the same as ej kei star. You switch the order and take the star. So it is the same. But what is this Ej Kei? This I can write as Ej from, where have I written that? Excuse me. From the blue color box, I know that K acting on alpha is the same as the vector K alpha. So the vector Kei is the same as K acting on Ei. So to go from here to here, refer to the green box. Okay, and this is the same as Ej Kei. To go from here to here, refer to the blue box. Okay, I should have probably made it blue and red matrix style, but it's okay. Now, what is star? I forgot the star. Yes, but what is EJKEI? It is the matrix element of K sandwiched between A, J, and I star. Okay. So from all these manipulations, you have understood something that you've probably understood 7 years ago. If you take the adjoint of a matrix, this is the same as changing rows into columns and columns into rows and taking the complex conjugate, right? So the matrix elements of the adjoint operator in the EI basis is the corresponding matrix element in the for the K operator transposed and complex conjugated. This is usually is how you define the Hermitian conjugate. So sometimes you also refer to the adjoint as the Hermitian conjugate of K. Okay. But in general, K dagger, the operator that acts in the dual vector space, is called the adjoint of the operator that acts in the linear vector space. Okay. So this is also a very important equation. So I will box this one also. All right. Are there any questions about any of this? Because now I want to move on to the subject of two important operators that you will encounter in quantum mechanics quite a few times. But before I move on, are there any questions about any of these manipulations that I have done here? Any questions or any comments that you have?
Sir?
Are things easy to follow, or are the manipulations looking a little weird? Can you unmute us? You can unmute yourselves.
Hello.
I don't want to unmute everybody because you will not be able to hear anybody. If you want, you can unmute yourself. I'm not able to hear you though, Sachin. No, your voice is very feeble. Why don't you?
Hello.
Yes, now it's better. Go on.
Yes, sir. I'm asking that yeah, the thing that you have written K dagger Ij is equal to EI, the upper one, sir. Can you go a bit up?
The first
you have written EI K dagger into KJ, right?
EJ.
But sorry, EJ. But sir, the product of EI and K dagger would be KEI, right? But that would be another vector.
Sorry, can you say that again? What do you mean?
Sir, EI and K dagger, the dot product, the product would give another vector in the dual vector space, KEI.
So by definition, the K dagger that I have written here acts on the bra vector.
Yes.
Okay, the K acts on the ket vector.
Sir,
Okay.
so at that time, we will get another vector that is KEI, right?
Which equation are you referring to? That will be easier.
I'm referring to the one that you have written, refer to the green box, the
Refer
below
to.
one.
Huh. Okay. So I have
It's
written EI K dagger EJ.
then you have written KEI EJ, right?
Exactly.
So
Yes.
I'm saying that KEI
Hmm.
is is a vector, is some vector in the dual space.
Absolutely.
Okay. So then how do you when you did the transpose conjugate,
Hmm.
then you wrote in the third line refer to the blue box, right?
Hmm. Hmm.
Sir, then at that time how do I know that this vector in the dual space when conjugated
Hmm.
would be the same as the one that you are referring to, the blue box?
Okay. So the question is, suppose in the first line, when I go from EI K dagger EJ to KEI EJ, the bra KEI is one vector in the dual vector space. EJ is another vector in the linear vector space, right?
Yes, yes,
Now I am using the definition of inner product to switch the order and take the complex conjugate, right? Now remember the definition of what a dual vector space is. For every gamma in the linear vector space, there exists a dual vector gamma in the dual vector space. Yes? Agreed?
yes,
Okay. Now, viewed in this sense, it should not be surprising that so suppose I have K dagger Ij is KEI EJ. This part is clear?
yes,
Okay. Now, remember that I can piece this up into the bra KEI times the ket vector EJ,
yes.
right? Now, this should have a dual in the linear vector space that is given by KEI. Agreed?
Okay, okay, sir, I got the point.
So every vector has a corresponding dual vector. So it is not surprising that this complex conjugate would also correspond to a vector in the linear vector space. Yeah? Makes sense?
Yes, yes, I got it.
Okay. Devanshi says, sir, will you give an example to explain this? Okay, sure. Uh, the example would be very trivial and you will be disappointed. The example is the usual definition of matrices. Okay. So let us take a two-dimensional example. Let us take a two-dimensional linear vector space. Okay. Now let us say that my linear basis vectors are 1, 0 and 0, 1. Okay. And let us say that in this vector space, my K operator takes the form, tell me anything, 1, 1 plus I, 2I, 3I plus 8. It doesn't matter, right? Now, what does this mean? So again, I'm going to mute all of you simply because you might have trouble hearing me. But if you have any questions at any point, please unmute and ask. Now, what does this mean? This means that my ket space is composed of vectors alpha of the form a1 times 1, 0 plus a2 times 0, 1. In other words, they are column vectors of the form a1, a2. And for every column vector in the ket space, there exists an analogous bra vector, row vector in the dual space. And I'll assume in this case that the vectors are complex. So the corresponding bra vector or row vector in this case is a1 star, a2 star. Yes. So the claim is that the K acts on the vectors a1, a2. Right? So what does this mean? This means that K 1, 1 plus I, 2I, 3I plus 8 acts on the vector A1, A2 to give you some other column vector. Right? Whatever it is, you can easily multiply and figure it out. So by this construction, I should figure out what is the corresponding matrix that acts on the row vector. What is the corresponding matrix that acts on the row vector? The corresponding matrix that acts on the row vector is K dagger, which is KJI star, which means I should take the K matrix, and then I should transpose this matrix, and then I should complex conjugate this matrix to understand what is K dagger. So K dagger in the same basis 1001, another, but in the basis actually row vector 10 and row vector 01 would be given by 1. If I transpose it and complex conjugate, I'll get 1 minus 2i, 1 minus I, minus 3i plus 8, right? And the claim is that the K dagger is the stuff that acts on the corresponding dual vector space, and I should act it on the right and not the left. And this is also in line with the usual rules of matrix multiplication, because A1 star, A2 star acting on 1 minus 2i, 1 minus I, minus 3i plus 8 gives you another row vector. Okay, this is a trivial example of what I am talking about. Is this clear? Okay. So I'll make a very important announcement, not about the course, but about these matrices in general. So it is okay to, at this point, it is okay to think of all matrices as operators. So in other words, whenever I say this operator has this matrix form, you immediately know that the adjoint of this matrix is based. Once you know the matrix, you know the adjoint, because it's just transpose and complex conjugate. There is no problem. But when we talk about function spaces, we will generalize the concept of operators to other kinds of objects like differential operators. Differential operators. Okay. And when I talk about differential operators, the adjoint of an operator cannot be so easily guessed like in the case of matrices. Okay, I'll have to construct the adjoint of an operator by appealing to one rule. I know, I'll tell you what this rule is. This rule is basically this, that the inner product alpha beta is the same as beta alpha star. Okay, but first I should define the notion of an inner product in function space, and then I will apply the condition or constraint that the inner product of two vectors alpha beta is the same as the inner product of beta alpha complex conjugated. And this rule will tell me how to compute the adjoint of differential operators. For example, to give you something that might look a little surprising, in the usual what is called the L2 space, or in the usual L2 space, I'll define what L2 space is later. The adjoint of the differential operator ddx, okay, this is just ordinary differentiation in one dimension, is actually minus ddx. Okay, so the rules that you have for simple matrix manipulations are not quite the same that you would follow for differential operators. In this case, in the case of operators as matrices, it is actually quite easy, because matrices do have this property of transpose and complex conjugation, and you can understand the adjoint of matrices in the usual form, but you have to understand the adjoint of differential operators in a slightly different fashion. I will explain what this is in the next class. Okay, so please ask me if there is any questions. If not, I will talk a little bit more about things that you probably already know.
Sir,
There is, yes.
Sir, I had a trivial doubt that when you wrote the equation K operator acting on alpha, alpha is equal to K alpha, which is a vector, right? And then you wrote the equation bra alpha acted by K dagger, right, is equal to bra K alpha. Sir, here what you did was smartly that K alpha, you named it as K alpha, right? If you had named it as something as something another another character, right? Then the way you did the other manipulation, one couldn't have guessed that it would be the dual. It would be a bra from the dual space of the cat.
No, you couldn't have. But what you could have guessed is, suppose if I called, instead of K dagger, if I had called it some B. Okay, in fact, this is what I would do when I talk about differential operators. I will not call it K dagger because it is confusing. Okay, I'll call it some other operator, some completely new operator B. Now you can go ahead with the same calculation, okay? And then now this alpha beta equal to beta alpha star becomes a constraint equation. So now you demand that whatever new operator that you wrote down, instead of k dagger, let us say you wrote some b, right? Should be such that if I take any inner product alpha beta, okay, and I compute beta alpha star, I will demand that this equation holds true. And this demand would actually tell me that the B operator should be exactly the K dagger that I have defined. In this case, I've cheated a little bit because I've assumed it in the initial stage, right? But look, in my formulation, suppose if I did not just take K dagger and I took a random vector B dagger, the only thing that will change is that whatever I've assumed to be true, trivially in the case as a definition of inner product will become a constraint equation. Okay, and this constraint equation will necessarily tell me that the operator B that I've defined on the bra space is actually equal to K dagger.
Okay, there. Okay.
So in the case of when I do the differential operator case, this should be clear to you. I will exactly start as you just told me. I will not start by saying this is some K dagger because I don't even know what DDX dagger is, right? So this is a very strange object. Again, my stop sharing is not working. So share the screen again. Sorry about that. And then I will show it from scratch that this is indeed true. Okay, that's a very good point. Any other questions or comments? Okay. So I will end today's lecture by telling you two things that you've probably seen before. There is two important classes of operators in quantum mechanics. Unitary operators and hermitian operators. Okay, let us talk about unitary operators first. What are unitary operators? So the definition of unitary operators is as follows. Suppose if I have a unitary operator U, okay, then the definition of unitary operator is the adjoint of the unitary operator times the unitary operator. And this is the same as U times U dagger is an identity operator. Okay, this is the same as what you mean by unitary matrix in usual linear algebra, that a unitary matrix U is 1 for which U dagger U equals 1. But what does this mean in quantum mechanics? In quantum mechanics, this is actually a very important class of operators for this particular reason. As I will tell you, quantum mechanics is formulated on the basis of certain postulates. And one of the postulates is that the state of a physical system, the first postulate is that the state of a physical system can be represented as a vector in a linear vector space. Okay, just like in classical mechanics, the state of a physical system is represented by the dynamical variables R and T. R basically, if you know R is a function of T, you have solved for the dynamics of a classical particle, right? So similarly in quantum mechanics, you have to understand how the vector that is describing the physical system evolves dynamically. In other words, the vectors in the linear vector space that describe a physical system in quantum mechanics are actually functions of time. Okay. Now, how do you understand how the vector evolves in time? Well, you understand it by claiming that you know what the vector is at time t equal to 0, and then you act upon this vector by an operator, okay, by a very specific operator called the time evolution operator, and this gives you the vector as a function of time. In other words, the time evolution operator, time evolution operator, acting on the vector at time t equal to 0 gives you the vector at time any other time t. Okay, we will later figure out that this is what is called the Schrodinger equation. So Suppose if I know the initial vector at time t equal to 0, I know how the vector evolves in time. Now, suppose if I want to calculate the overlap or inner product of two vectors, beta of t, alpha of t, okay, at any time t. Now, what is the corresponding Bra equation? I can write the corresponding Bra equation as u dagger equals alpha of t, okay. And now if I plug this in, I will get the Bra B transforms according to B0 U dagger. The ket alpha transforms according to U alpha. And if the time evolution operator is unitary, in the sense that U dagger U is the identity operator, this is the same as B0 alpha 0. In other words, the time evolution in quantum mechanics is governed by a unitary operator, and the implication of this is that the inner product of vectors in any linear vector space does not change with respect to time. The vectors themselves change with respect to time, but the inner product of two vectors does not change with respect to time. And we will later find out that this inner product is related to the probability of measuring something. Okay, it's called the probability amplitude. So in other words, as long as the time evolution in quantum mechanics is guaranteed to be unitary, then we can understand that the probability amplitudes are time independent. We will talk more about this when we talk about the postulates of quantum mechanics, hopefully in a couple of lectures from now. I would need a couple more lectures to polish off function spaces. Okay, so this is why unitary operators are of fundamental significance in quantum mechanics. There is also another reason which is a little more advanced, but I'll just mention it for those of you that might be interested. So another thing that is of fundamental importance in quantum mechanics is group theory. Basically, a very, very smart mathematician / physicist called Eugene Wigner proved that there is only two classes of operators for which this preservation of probability amplitudes is true. Okay, one of them is a unitary operator, that the other is an anti-unitary operator. An anti-unitary operator, which you can easily guess, is one for which U dagger U is -1. Okay, this is actually a very, very easy statement to state, but it's quite a difficult statement to prove. Okay, so okay. If you understand the relation between quantum mechanics and group theory, and I will talk a little bit about this very beautiful subject of the connection of quantum mechanics to group theory in your second semester quantum mechanics course, if I'm still teaching it, then we will talk a little bit more about this beautiful connection and the beautiful mathematics underlying it. Okay, so unitary operators are of fundamental significance in quantum mechanics. The other thing that is of very fundamental importance in quantum mechanics is hermitian operators. And for now, since we are not dealing with function spaces, you can understand hermitian operators as those for which the adjoint of the operator is the same as the operator itself. Okay. In fact, this is also true in the case of function spaces, but you have to carefully figure out what the adjoint is. You cannot just take a matrix and complex conjugate and transpose it, because there is no matrix to begin with. Okay, so Hermitian operators and unitary operators are two classes of operators that are of fundamental significance in quantum mechanics. And the reason why Hermitian operators are very important in quantum mechanics stems from a very, very, very basic property of Hermitian matrices. The eigenvalues of a Hermitian operator, or equivalently a Hermitian matrix, are real. The matrix itself could be complex with complex entries, but the eigenvalues of a Hermitian operator are real. Okay. Now, what this means, and there is one other fundamental property of Hermitian matrices, the eigenvectors are orthogonal to each other. Both of these are of fundamental significance in quantum mechanics, because all operators in quantum mechanics that are of interest, In other words, all operators in quantum mechanics that represent observables that can be measured in a laboratory can be, are expressed, not can be, are expressed as Hermitian operators. And since whatever you measure in a laboratory are real quantities, you don't measure the conductivity of a material to be 2 plus I, right? You measure it to be 1, 2 with some units. So you want the results of experimentation to be real quantities. So it is crucial in quantum mechanics that all operators that deal with observation are dealt with by Hermitian operators because their eigenvalues are real. This sounds like a cryptic statement right now, but it will become more precise as I talk more about the postulates of quantum mechanics in the coming classes. So I will stop here. This was basically a rough introduction, not a rough introduction, a semi-detailed introduction to the theory of operators and quantum mechanics. We will talk a little bit more about Hermitian operators in the next class, and then we'll move on to the notion of function space. And hopefully by the next week, we should have all the mathematics in place for us to start dealing with the postulates of quantum mechanics. I will state the postulates of quantum mechanics and make them precise. But since you hopefully understand all the associated mathematics already, understanding the postulates themselves should be quite interesting, but maybe not straightforward. So that is the rough plan. So I'll stop here for today and ask if there is any final questions that you have. You can unmute yourselves and ask, or you can type in the chat window. I will formally stop the lecture at this point and ask if there's any questions.